Welcome! In this lecture I'll go through the kinetic equations and how they can be used to derive the two fluid equations of plasma physics. This is partly a review of what was done in a previous lecture on the Euler equations, but I'll show how that can be extended to plasma equations, because there are some slight subtleties and changes that go from when you go from fluids to plasmas. But hopefully this will be fairly familiar and we'll just go through and see what the changes are. So we start with the Boltzmann equation, the same as for fluids, but now we have a slightly different force because we have the Lorentz force on the particles, and we have of course changed different collisions, and so I'll just write down in here. So we have the Boltzmann equation, where here we have the distribution function f, where f is essentially how many particles occupy a particular volume in phase space, so it's something that's changed in time. It depends on the location in space, and it depends on a kind of location in velocity space. So I'm using v here for the velocity dimension, and then u to mean later on we'll see as a fluid speed, so as a velocity that changes in time. So this is a coordinate just like x or t. And so it's a 7-dimensional object, and it obeys this equation. So here we have advection in space, so velocity moves particles around in space. This f is the force, and it moves particles around in velocity. So this here you can write as essentially multiplying out these components. This is just each component of this expression multiplied out. So the force in the x direction moves particles in x, in the velocity in the x directions. This is v subscript x, just means velocity in x. The same in y and same in z. And then this side here is the collisions, which I won't go into much detail in this talk, but I'll cover in a later lecture. So from this equation we can derive fluid equations, but first we need to put in an expression for this force. So in plasmas, the force we're mainly going to consider is the Lorentz force. So it's the charge, you have the electric field, and the magnetic field. So it depends on the force depends on the velocity perpendicular to b. And now E and B are time-dependent quantities which vary in space. And these of course couple to Maxwell's equations. So if we want the full system of equations, we need Maxwell's equations for the electric and magnetic fields. We need this equation for F, and then from F we can calculate the charge density and the currents, which go back into calculating Maxwell's equations. So it forms a closed system, just a very complicated system. And so for fluid equations, we can take moments of this equation. And so the first moment is of course the density, and this is the 0th moment of this Boltzmann equation, because we're integrating while multiplying by v to the power 0, so just multiplying by 1. And we have the density, some function of time and space. So this is number density, so it's how many particles are there per cubic meter, for example. And this is just the integral of f, which again is a function of time, space, and velocity dimension. And we just add up all the particles at any velocity at a given location. And so we just integrate over these velocity dimensions. And so here I'm just using this to mean dvx, dvy, dvz. So this is a triple integral over all components of the velocity. And so we can work out the time derivative by integrating this Boltzmann equation up here. So we just integrate this whole equation in v. And we can quickly identify that this first term is just the time derivative of this density. So this first term here is just dn by dt. This second term here, because the velocity is a dimension, it doesn't depend on space, and so we can move this velocity in or out of this divergence. And so you can just write this as the divergence of the integral of v times f dv. So this is a derivative in space, and these things, only f here depends on space. V is a dimension that doesn't depend on space, so this can come outside. This is a divergence. And this is the next moment. So this is the first moment which is the velocity times the integral of the velocity times the distribution function, and this is the speed of the essentially the flux of the particles. So it's the average fluid flow velocity, which is called u, times the density. And this will need another equation to calculate. So we'll need the momentum equation to calculate what this is. This equation here, this again, because in this case the force is perpendicular to the velocity, we can actually manipulate this. I'll show you how this works. So because the force here is in the direction perpendicular to the velocity, we have that for example the force in the x direction does not depend on the velocity in the x direction. So this is true for all the components, because the force is always perpendicular to the velocity. And so we can, for each of these components here, we can move the force into or out of this derivative here. So we can move this derivative d by dvy onto the outside of here. And so we can just rewrite this term. This term can just be rewritten as a integral of d by dv dotted with f over m times distribution function f dv. And now this term is essentially like a volume integral, except rather than labeling it space, we've labeled it v, but it's a triple integral, a volume integral over a divergence. And so we can just use Stokes' theorem that this can just be essentially a surface integral over this part here, and it's a surface integral as velocity goes to infinity. And so this part here goes to 0 when velocity goes to infinity, because the distribution function goes to 0. And so this section here, this goes to 0 because f goes to 0 at the limits. So if you're doing the surface integral in velocity space, you can push the surface as large velocity as you like, and so f goes to 0. This is for velocity goes to infinity. So magnitude of the velocity goes to infinity. Now this last term here, this is the collision term, and this essentially is 0 in most cases we'll consider here. So this is the source or sink of particles due to collisions. It could, for example, be ionization or some kind of atomic reactions, some kind of source term. But for now we'll assume this is 0 if the particles are conserved. But it could be non-zero if some types of particles can be converted into others. So if neutral atoms can be converted into plasma ions, then this might act as a source. Okay, so then we have all the non-zero terms are so dn by dt. Then we have a divergence of the flux. This u times n is 0. No, that's exactly the same as the Euler equation. The only difference being that I wrote that in mass. So if you multiply this through by a mass, this will become a mass density and a mass density, and then it'd be exactly the same. So now we need to calculate what this flux term is, un, and this is the momentum equation just as it was in Euler's equations. And so we need the first moment of the distribution function. So this is the fluid speed, which is some function of time and space, and this is the first moment. So we have v times f, which is some function of time, space, and velocity, integrated over the 3 velocity dimensions. And so we multiply through the Boltzmann equation by v and integrate it, and so we end up with the integral. So many of these are the same as for the Euler equation. So first on the left hand side, of course the time derivative comes straight through on the outside because the velocity is a dimension, and so it doesn't depend on time. And so this part here is just d by dt of u times n. This part here I covered in the earlier video. We can just write this in various ways, but it's essentially the stress tensor. So we can pull the divergence outside here. So it ends up being the divergence of of the next moment, dv, and this is the stress tensor. We can then also write this in terms of relative velocity. So we can define a relative velocity w is the velocity minus the average velocity. So the average of w is now 0, and then we can write this in terms of an advection of momentum and a pressure tensor. So this term here, and in this case, this gives us an advection of momentum. Here we have this is the pressure tensor. So this part here is pressure. We actually need a mass in here. So if this was momentum, there'd be a mass, and so this actually needs is pressure divided by mass, and they call m for the mass of the particle. Okay, and then so this is pretty much the same as fluids. Of course, for a plasma, the pressure tensor will be different because the plasma has different properties. Particularly perpendicular to the magnetic field, be very different from a fluid. But the basic structure of the equations is similar at this point. The tricky bit I'm going to cover quickly is this part here. So the force term, and it's easiest to just see each component separately. So if we first look at the x component of this equation. So I'm going to take this force term here, and then just take the x component, because then the same calculation works for the y and the z components, so it's easier to see where the equation comes from. And so I can just write this out. It's going to be a bit long to start with, but will get shorter. So we have the velocity in the x component from this, and then this is a dot product. This expands. Okay, so the first thing to note is that this is a three-dimensional integral over vx, vy, vz, and so we can take, for example, this term in the middle, and we can integrate it first in vy, and now vx doesn't depend on vy, so this just becomes an integral of this piece over vy, and then that's just the same as the density equation, and so that term goes to 0. So this term goes to 0 because f goes to 0 as velocity goes plus minus infinity. So this goes to 0, since f goes to 0 for vy goes to plus minus infinity. Yeah, because this term here can be converted into a volume integral of a divergence, and then turned into a surface integral and goes to 0. And the same for the z direction. This one also goes to 0. Because we can pull this vx out and just make this an integral in vz. So we're just left with this term at the beginning, and this term I'll write again just so you can see it more clearly. So we have this term integrated over overall velocity. So this we can split up. So now we can put in the force. So Fx is the charge times the electric field plus the charge times velocity cross b. And if we want the x component of this, I'll just write that like that. So this is qex plus q, so vy bz minus vz by. So it's written out explicitly all the components. And so we have that this integral can be split into two pieces. So first just take the ex component. Now electric field just depends on time and space, it doesn't depend on velocity, and so it can be pulled outside. So we get a q over m times the electric field in the x direction, which I've pulled outside, multiplied by this vx. We have df by dvx dv, and then this velocity term is a little bit more tricky, but again the charge will come outside, and then we'll deal with the rest shortly. So we have the force term, we have the velocity in the x direction, and the f by dx, dvx. So this kind of term appears several times, so we can first consider what happens to this. So again, this is a three-dimensional integral over vx, vy, vz. So we take the vx component first. So we say this is the integral vx dvx, and then we can integrate this with vy dvz as well. So just taking this first part, we can differentiate this bit, integrate that part. We end up with so we have a vx times f and dvx, well, vx going from minus infinity to infinity, and then this differentiated of course just becomes 1. So we just have that left over. And this is the integral in dvx, and then we integrate this in with vy vz as well. And so this whole thing just becomes the integral of f dvx, and then dvy dvz from here. And so this whole thing just becomes n. It turns on time and space because we integrate it over all velocity. So this is the number density. We can do the same trick here. So vy's and vz's, and none of this depends on vx. And so we first integrate this part here with vx, and we end up with the same thing, that this, so the integral of this dvx, so this becomes the integral of f dvx. And then we integrate the whole thing over dvy dvz. So what we end up with, if I write this out, so the first term we have is just q over m ex times n. So this is this first term. The second term here, what we have, if I write out the integrals explicitly, so we have an integral over vy vz, so vy vz minus. So now this this integral here over vx, this has just become f dvx, and then these outer integrals are vy dvz. Okay, of course this now splits up into two pieces. So when we integrate over vy, we'll pick up this vy here, and so we end up with a term. So here we end up with a term which has an integral of vy. So we just have vy times f. And we can just put all the v's back together again, so it just becomes a dv. And this multiplied by pz. And this term becomes an integral of vz times f over v multiplied by vy. Okay, so this is here is just n times u in the y direction, and this is n times u in the z direction. I've realised I've missed out a minus sign here because this term here has of course a minus sign at the front, and so this all flips sign, so with a minus sign here, and this term here in the e direction, this also picks up a minus sign. Apologies, so there should be a minus sign in front of there and a minus sign in here. So here we have a minus, this would be a minus, and that would be a plus, so a minus of a minus. Okay, so this whole thing, now this is just uy, the fluid velocity cross bz, and this is uz cross by, and so this whole thing is just q over m plus now the fluid velocity crossed with magnetic field, and here I'm just looking at the x component of this force, and the whole thing picks up a minus sign from this partial integration. Okay, so this is what the term, go back to where we started, we were trying to find out what this term here looks like, and it ends up looking actually quite simple, that we just end up with the Lorentz force, except with the fluid flow replaced by the particle flow velocity v replaced with the fluid velocity u. And so the whole equation now just looks like d by dt of the momentum without the density plus the divergence of this flow term that came from the v term, the second moment. And that also brought with it a pressure tensor term. And then then we had this term here from the Lorentz force. So this is Q over m. And then we have the collision terms. Now these may depend on other species, so collisions between different species. And so this is quite often just called R. There's some force from collisions. There's collisions, some kind of friction between species or with itself. So from here we can continue to higher moments. So you can calculate this term here from integrating the second moment, and that will get you an equation for the heat, for the internal energy. So if you want a temperature equation, what we can also do is we can close this equation by just assuming adiabatic gas laws, which is what's done for ideal MHD, for example. There's also a whole lot of unknowns in here, so this pressure tensor, for example, and these collision terms. So if you were to do the Brzezinski ordering, and I'll do in a later video, go through how these are actually calculated, or we can simplify them and make some approximations, and that we'll do in the next lecture on how to derive single fluid equations. But this equation here, for example, describes the equations for a single species. So this could be electrons, or it could be ions, and so usually these equations are used for multiple species, in particular two species. So you might have ions plus electrons, and so these are equations for two fluids. It's called. So these are equations for each species separately. And therefore they're called the two fluid equations, and you can extend this to higher moments fairly straightforwardly. The math starts to get a bit longer, but once you've got the hang of manipulating these vector quantities, it gets much easier. Okay, so next video I'll go through how these equations are simplified and turned into ideal MHD. Okay, thank you.